Hi everyone, and welcome to Automated Software Refactoring with OpenRewrite and Generative AI. In this talk, I'll take you through our experiences at Modern in working with Generative AI as a company that aims to make reliable code changes at scale. That might then seem like a contradiction to use AI, but we're going to look at how we've made that work. I'll hope you learn from our pragmatic approach to generative AI to see how you can leverage the same technology in your work. First up, this is me. My name's Tim de Beek, and I'm a staff software engineer at Modern, where I'm the community lead for OpenRewrite. In this role, I help folks get familiar with using OpenRewrite and extending the recipe catalog for their own needs. I also work on the tooling that we offer at Modern to aid developers, such as the CLI, the IntelliJ plugin that we have, and the Modern platform. I'm a big fan of contributing to open source software, as you can see from the green bar at the bottom. I should probably take more days off. But once in a while, I do present at conferences or online, such as here in Barcelona. But more importantly, this is not me. This is my brilliant colleague, Justine, who's done all the hard work that has gone into this presentation. She's our AI researcher that works at the Mila Institute in Montreal, where she collaborates with other researchers to bring AI to OpenRewrite and Modern. She's doing a lot of groundbreaking work for the company. So much so that, unfortunately, she has become too important to get flown out to Europe, which is sad for her and all of you, but it's good for me. The lesson here is don't get too smart so you don't miss out on Barcelona. As a good sport, she has provided me with notes to follow along for this presentation, and she's offered to bring her on virtually at the end if there's any questions. Now, we both work at Modern, which, if you're unfamiliar, we are the main sponsors of OpenRewrite. We offer tools and a platform to run code modification recipes at scale across your organization. That way you can update dozens or even thousands of projects at once in mere minutes. And as you can see, the OpenRewrite logo and the Modern logo, they are very similar, but not a lot of folks have figured that out. Just saying. The code modification recipes are OpenRewrite recipes that allow you to safely match and modify your code. If you have never heard of OpenRewrite, then congratulations. You've already learned something valuable today. But you've also not been paying attention, because I've been telling folks that you can do automated upgrades of Spring applications for 3 years now. I was in this very room 2 years ago on my birthday telling folks that you can do these types of upgrades with OpenRewrite. And that's taking you from Spring Boot 1.5 on Java 8 to just Spring Boot 3.3 on Java 21, picking up JUnit 5 and Jakarta along the way. All of that is using open source software developed with help from the community. So while I'll briefly show you some of this as it relates to our work on AI, I'm not going to repeat last year's talk. Instead, come to our booth or the workshop that I'm giving tomorrow to learn more about OpenRewrite. Very briefly, if I'm going to talk about automated code modifications, I like to show this example, which is taking you from JUnit 4 to JUnit 5. Now, as you've probably learned, when you upgrade from Spring Boot 2 to Spring Boot 3, you have to update to JUnit 5. In the past, if you wanted to assert an exception was thrown, you had to add that to the annotation, whereas nowadays you have to call a different method using that same argument and do a slightly different flow in that way. Now, this is a type of change that you're unlikely to be able to do with a regular expression. So what we have done is we have built a technology that allows you to do such safe code modifications by building up a very detailed model of your code. This model contains extensive type information, which we use to match elements of the lossless semantic tree that we built up. And we then use the visitor pattern to traverse that model and modify it before writing out the changes as closely as we can get to the original source code. And we use this to automatically migrate a host of languages and technologies, such that you can upgrade or you can secure your applications and you can improve code quality. Modern then runs these same recipes at scale, both for the wider open source community and for our customers. Such that if you have 1 million lines of code to maintain, we make that easy through the Modern platform and surrounding tooling. That also means that there is a lot of trust involved. When you make changes across millions of lines of code, things should just work. That way you can, but you shouldn't have to review any of the lines changed, as you can see on the right. Customers then come to Modern to make it easier to manage their software. And while we have both small and larger customers, often these are large financial institutions. There's a good chance if you open your wallet, you will find 1 or 2 in there. And these customers, they like predictability. They want accurate and repeatable code changes. And if you had 1 million lines of code to maintain, so would you. Now, interestingly, we have found that these types of customers, they either love or they hate unpredictable AI. We've had customers distrust AI and ask us to disable all AI features. And on the opposite end, we've had prospective customers who would love to buy Modern, but they only have budget for AI. So that makes for an interesting mix to then build out these capabilities. So in that context, we are going to look at AI, a technology that is very much unpredictable, and yet still try to get value from this for our users. Ideally without massive expense, because we are a startup after all. And we've also had to work our way back through the very bundled experience that is AI these days, to something that we can actually use in our platform. I'll take you through our experiences working with AI and how that has pretty much followed the hype cycle. You've likely seen this trend before, where for any new technology, there is a brief period where things get kind of wild. We'll look at what we tried when we first started and how we massively scaled back our expectations. And then I'll show you what we have arrived at since in our use of AI. So when OpenAI and ChatGPT first became available, we had high hopes for generative AI. We had some 1,000 recipes in our catalog back then, and we have since doubled that number. And yet still, there is a lot more ecosystem to cover with recipes. Previously, we had folks be amazed that we could automate any part of their upgrades at all. Nowadays, we get complaints that we don't upgrade their very niche library, which is an interesting problem to have. So we set out to generate our first AI recipe, and the results, they did look convincing. But when Justine asked a colleague to review the recipe, we found some very clear problems. The first one is that the recipe did not compile. And not only that, a lot of the methods did not even exist. And it had no sense of using the visitor pattern that we use to traverse the LST. And these types of confabulations or hallucinations are a common occurrence when using generative AI, and they are very hard to combat. Clearly, this was terrible for our use of AI, and we had to massively scale back our expectations. So next up, we set out to get a limited amount of generated code for a very particular use case. In this case, making sure that the default case in a switch statement comes last. This is an existing check style rule, and we already have a recipe to cover this. It's also a case that is very easy to explain, but it needs some thought to actually get right. You'll want the default case to come last for readability, but you don't want to change the function while you do so. So you need to reorder the statements that you have and account for fall through correctly. And we had the unit tests for this recipe already. It's pretty simple stuff, but let's see how OpenAI does. With a bit of plumbing, we hooked up our visitor pattern to the OpenAI API. We visit every switch statement there is, and if we find a default case, then we send the whole switch statement over to OpenAI. We include an instruction to place the default case last, as you see highlighted near the bottom. We swap out any response we get, and hey presto, we are done. When you run this recipe, it kind of works, sort of. That's if you run it once, you might get lucky. If you run it twice, it might get a different response. So it's kind of hard when you're asserting your tests have a certain output. And if you run it 100 times, you are definitely in trouble. So some of the failure modes that we saw was that other case statements suddenly got reordered as well, and fall through was not handled correctly. And we can kind of mitigate these patterns by being very clear with the instructions that we give it. So maybe tell it to not change the order of any other case statements, or keep the logic exactly the same. But this seems like a lot of work, and it might still get things wrong. Clearly, this is not ideal. And remember, we are operating across millions of lines of code. Recipes can be run repeatedly, and so ideally we see the same results every day. Definitely not shuffling the case statements around every day, as you do. So remember when I said that our customers like predictability, and that things should just work? Well, we were very much heading towards the bottom of the trough of disillusionment. There is a lot of promise in the technology, but so far it's been failing to materialize. So what then is a good use case for us in using AI? What is the minimum viable project that we can deliver that still proves some value for the customer? Well, we had a customer come to us with a very interesting use case. They are a big French-Canadian company, and as per their local laws, they have to code in French. This extends to Excel functions and code comments as well. So to check their compliance, we used a very small open source model to detect the language used in the comments. As you can see here, we have a visitor pattern that visits any comments, and from there calls out to a small sidecar model to detect the language used. And this alone was useful to gain insight into their use, but it also allowed us to fix a problem that they were having. Because being a big Canadian bank, they also had a lot of changes made through the source code over time, and one of those was that they frequently switched encodings. And that is okay if you're using plain old English, but if you're using French accents, then suddenly you'll end up with some invalid characters, like question marks or Unicode kind of glyphs. And worse still, this meant that their Java doc generator failed to parse these comments, and as a result of which their internal libraries were lacking in documentation support in the IDE. So while we were already able to detect the language models, we now set out to make a recipe that looks across those comments, finds any misencoded characters, and then swaps in the closest match that we find in French. So we now have a recipe that can fix these encoding issues, and that leads to better readable code and the ability to compile the Java doc for a better result of these libraries downstream. If you want to read more about this use case, we have a blog that goes into more detail, and it shows that we now have recipes that can individually leverage AI to achieve their goals. And we have our first use case for AI in an application. We are slowly looking up to the slope of enlightenment on the hype chart that we have. Now next up, we had a search option that was pretty mediocre. And with now 2,500 individual recipes, that was starting to hurt us as well. Coming from a Java background, we had a search that was based on a very old Lucene. And while that does support some word stemming, it does fail to find synonyms. And if you have a lot of recipes, it's not always clear if you should be looking for change dependency or bump dependency, update dependency, upgrade dependency, migrate dependency. There is a lot of variability there, and it's not always clear what you should look for. Sometimes users and customers would wrongly conclude that a recipe did not exist, or even create functional copies of existing recipes. And we've done this ourselves as well. I've had multiple cases where I found a recipe that we already had. So if you know exactly what to look for, then keyword search is okay. But if you're new to the project, you could use a little help exploring. And rather than upgrading to a new Lucene, we figured that we could improve our search through the use of AI. Now, our very first attempt at this was very naive. We used an open source model locally and asked it to pick a recipe from the complete list. We pass in a query that the user had entered and our 1,000 recipe descriptions, and then parse the results. But this didn't work very well. The model would get confused about the size of the input tokens. If you put 1,000 recipe descriptions in there, the query would get lost in the noise. And it again started to invent recipes that weren't there, which isn't great if you're doing a search. And it was slow. This is search that we're aiming for, something that gives you an immediate response, not tell you to come back in a minute or two. So for our second attempt, we went back to the documentation and we looked at a retrieval augmented generation. For this, you turn your search terms into a multi-dimensional factor, which is exciting stuff. You enter a query and out comes some number. Then you look for numbers that are close in space, but maybe not identical. And consider, for instance, the two words love and hate. Those might be very different in their meaning, but they are both passionate emotions, which puts them close together in that multi-dimensional space. Now, this approach did look very promising in theory, but we had some test cases that we ran and we found that we got 1 out of every 20 correct. This was the absolute low point that we had in using generative AI for our research. We'd wanted to generate recipes, but we couldn't even get our search to work. So Justine then went over to her colleagues that she had at Mila to ask for input. And as it turns out, you can't use embeddings for search unless the model has specifically been trained for retrieval. And that is why it's great to have Justine at Mila, where she can leverage the collective knowledge of the fellow researchers there for our research at Modern. So then we set out to find a better model, and there are a lot of models out there. And it can be overwhelming trying to find the best one for your particular task. Thankfully, Hugging Face, which hosts many different models, also hosts benchmark leaderboards, such as the massive text embedding leaderboard that you can see here. We use this benchmark to identify potential models for our search. And as you can see, there are a lot of characteristics different between each of these models. Some of them, they use dozens of gigabytes of memory just to run. And others, they use just a few, and they might even have results close to each other. We've landed on a model that has since fallen out of this top 10, but it works very well for our use case. Now, our search is done in 2 steps. The first step is to retrieve from a pre-filled vector database, as you can see above here. And we fill the vector database with embeddings where each point is a recipe. When a user has a query, we can use the distance to figure out which of these recipes are most closely related to the query. Now, the second step is to re-rank the top 25 recipes returned from this first step. And this re-ranking also filters out any recipes that might have accidentally gotten picked up, where they should not have been. And the reason for this is two-step search is threefold. First, we can use a model, for example, the model in the second phase that cannot use cached vectors on a smaller search space. And second, it lets us use a larger model, going from a couple megabytes to a couple gigabytes on a smaller search space as well. And third, we can establish a threshold for similarity score that determines when a recipe and a query are considered related. As a last step, we optimize for the use case that our users will have. They are typically looking for the most recent, most valuable recipe to run. And in that space, we have composite recipes that contain more and more recipes. If you want to upgrade to Spring Boot 3, we first take you to Spring Boot 2 and Spring Boot 1, such that the recipe with the most contained recipes is going to be the latest one. So we let that bubble up to the top. such that if you get a number of results presented, you're most likely to find the one you're looking for near the top there. Now, if you want to read more about this approach, then Justine has written a blog exploring both our model selection and our deployment, as well as any of the runtime considerations that factored in. In terms of cost efficiency, we have chosen to have others train for us on their GPUs, while we run on CPUs in sidecars to keep the models in memory. And that way we're able to keep costs down as we go. Now, I want to show you briefly how this recipe search works in practice, and for that I'm going to take you to the modern platform. And that means I have to quickly switch screens, which I hope works. It's got a mirror. Sort of. So this is the modern platform where we're able to, can I zoom a bit? Where you're able to explore the recipes that we have. So when I told you that we can upgrade you to Spring Boot 3, we have one recipe that combines all of those steps for you. So that is our Spring Boot 3 best practices recipe. And what that does is it brings you first to Spring Boot, from Spring Boot 2 to Spring Boot 3, and then also enables, migrates you to Java 21, such that we can enable virtual threads. And all of this is a composite of some 2,000 recipes that you can run to get your own applications migrated. We've found that once in a while, folks will want to slightly tweak this recipe that we already have created. And for that, we have this recipe builder. If you go to app.modern.io/builder, you can use this to create your own composite recipe to do exactly what you want, and none of the steps that we thought would be helpful for you as well. And to expand on this, we can use this dialog to actually add a recipe. And this is what pops up our AI research box. Now this one, if you don't add anything, we have some suggestions, but in this case I want to add, for instance, a step to upgrade some Gradle GitHub actions that they have recently renamed. So I can add in some search terms, so Gradle GitHub actions was changed. And then the AI search will do everything that we said in the back, doing taking our query, turning it into a vector, finding any recipes in the same space, ranking them, throwing out anything unrelated, and present you with these 22 recipes that it thought would be most actionable. And while I used changed instead of rename, they did correctly identify that the top one is the one that I was searching for. So we can add this one to the recipe and then choose to download this modified recipe, add it to your own recipe library, and you're off running. You have your own custom recipe built with help of AI in this builder. So that's all well and good. But remember when I said that we have some customers that do not like AI? If you want to make Justine very sad, we have a button here at the bottom where you can disable all AI search. So don't do that one, but know that it's there if you need it. It's So with that, let's go back to the presentation. Previous interview. Yep. And displays again. What is where? To find my mouse. Yeah. Just a moment. And maximize. So, search is pretty good. It's now working very well for us, but we'd much rather not have you have to search for things. So if we could do recipe recommendations, that would be even better. No need for you to learn which of the 2,500 recipes we have. Ideally, we will just suggest what you want to run next. And that was our plans with doing recipe recommendations. So we set out to achieve this task, again using generative AI, but now using this prompt, where we say, you are a software engineer, what can you improve about this code? And then we would insert a snippet of code. Typically that would be a complete method declaration, and then you get back some recommendations. And we're striving for useful guidance here in natural language, not direct code changes, because we want to be predictable. We want to have it recommend a recipe, not recommend a direct code changes. Now this simple prompt already performed well, but there was one thing that made it a lot better. That is by fake it till you make it. If you are a senior software engineer, you get a lot better recommendations to do to these code changes. In practice, that would look something like this. We take a method, we feed it to the LLM, and out comes a list of proposed changes. And note how that in this case, we have a method that we put in, and the suggestion is to upgrade to Java 8 or later, because the Boolean class was introduced in Java 5, but has been deprecated in favor of the Boolean privilege. That is a load of bollocks. That is not true. But the nice thing is, if we take this description and we feed it into our recipe search, it does cluster together nicely with similar recipes in that space. So by having an additional step that looks for recipes near the query that we're looking for, we are going to get some useful output from this, this clearly wrong suggestion. But nothing's ever easy when you are running at scale. We want to recommend recipes for a whole business unit, and with our customers, that is typically large. So if you have a decently sized business unit, that might look something like this. We have some 1,200 recipes and a lot of contributing developers across some 62 million lines of code, and we want to do some AI recommendations. And for that, we are going to first extract the 400,000 unique method declarations, and then we're going to do some quick math. 400,000 method declarations, maybe some 3 seconds to get some recommendations for each individual method. Multiplied together, that is some 335 hours. Clearly, this is not going to work. No one is going to wait 2 weeks to get some recommendations, and even if we speed it up by 50%, that is still a week. That's just not going to work. So we need a way to sensibly limit the search space. Now you could do some random sampling here, taking 1 in every 100 methods, but that would kind of skew towards things that you have a lot of, like simple getters or a toString method. And that would not lead to a lot of interesting code patterns to do these suggestions. Instead, we want to get some more diverse sampling going to get you better suggestions for a more comprehensive recipe suggestions. And so for that, we go back to embeddings. We previously used embeddings for our recipe search, but we're going to now look at factorization of our method declarations. So we take those 400,000 recipes and we then cluster them together such that we can then sample across these different clusters. That way that if you kind of assume that if you take a representative sample from each of these clusters and you get some recommendations, that they will also apply to the other methods within that same cluster. So you can get decent recipes to run, which will make changes to all of those methods, just based on some interesting sampling here. So eventually we ended up with this workflow, where using the clustering we just showed, we do a diverse sampling. And then using the sampled method definitions, we use a model to generate the modernization recommendations. And we played around with a few different prompts here, but it's all around the themes of you are a senior software developer, tasked with finding modernization opportunities in this code. And generate me 3 recommendations. These recommendations then need to be verified. And as you saw in the Boolean example, there can be quite some noise and hallucinations. To remedy that, we then use our recipe search, as I have shown, and like that, so that whatever recommendations that we get, they are guardrailed by our recipe catalog. So you only get any recipes recommended that actually do something meaningful. As a next step, we're going to integrate this into a dashboard that we have, such that we run the recommendation pipeline on a schedule to make sure that no modernization opportunity is missed for the users of our platform, for open source software or anything you have internally. Now, once again, if you want a more thorough take on this approach, then Justine has you covered there. There's a blog that you can read into, and it goes a lot more in depth than what I'm able to cover here. But we can also look at some of these results in practice. And for that, I'm going to switch screens yet again. And that is this one. And then take you to, in this case, the recipe that we have to do this clustering. So when I said we take all those method declarations, this is the recipe that grabs them from whatever organization unit that you have, and then allows you to cluster them either by class or by method based on their similarity in that search space. Now we can run this, in this case, against some 12 repositories in this organization, and this will schedule it in the background. But I've also helpfully already done this earlier. So if we go to this next page, you can see that I've run this clustering against the OpenRewrite GitHub organization. And as you can see here, they have a lot of recipes, a lot of methods that are very similar, neatly grouped together by collapsing that multidimensional space into something that is a nice 2D representation. So all the methods to get a description grouped together, all the methods that get a display name, and then on the right here you can see that all the methods that do visits across the visitors that we have in OpenRewrite, they are also neatly grouped together. So there's some defaults in there, part of our search tests there, and then some random methods that altogether are something hard to pin down to anything in particular. But you can see with these clusters that you get a useful grouping of things, and if you only take a few from each of these samples, you will get a very meaningful outputs from each of your invocations of the generative AI, rather than having them select 10 different methods that each get a description. If we then run our recipe to get recommendations using this sampled embeddings, then we can sampled method declarations. Then we can get some recommendations out of AI. And let me briefly zoom in here. Then you can see that in this case we get again the same hallucinated recommendations for these method declarations. Again, going on about the Boolean class introduced in Java 5. But the other ones, they are pretty decent. They are going to find the recipes that we are actually looking for, and then suggest that you run those, and when you run them, you get the predictable code changes that we are actually after. So with that, we have our input for our search, and we are actually off to do some useful code modifications. So we get, in this case, we ran it against the OpenRewrite recipes, and some of the things that it recommends is to upgrade to Java 17, which, fair enough, yes, we are on Java 8, but that is because our customers are still on Java 8. So while I would very much love to run a Java 17 migration, I simply can't. But it has correctly identified that this is something that we could do and could prove valuable to help maintain this code. So then we have recommendations going as something that is meaningful for our users to be able to help modernize their code and not have to learn 2,500 recipes to do so. So let's jump back to the presentation, and I'm going to join to this place. And I'm going to drag this one here. And do this. And full screen. So, finally then, we have a last use case that we've been looking at and using generative AI for a useful application for our users. And the one that we settled on is code search. And this has been the most groundbreaking work that we've worked on to do an AI-based code search. And this is based on a customer request that reached us again. So we had a customer that was using a particular identity access manager provider. And that provider tried to hike their prices. They know exactly when they have you, and you can't really switch away easily. And then they try to double your bill and give you 2 months' notice. So this being identity access management, it was integrated all over the place, and as such they were looking at having high costs for a while before a painful transition away from this identity access provider. So as it turned out, they were looking into how can they actually move away from this, and all of these integrations were using a particular HTTP header for this IAM provider. But they had multiple different HTTP clients in use, so this proved hard to pin down with the existing recipes that we have. So we have recipes where you can find method invocations for a particular client, but not a client in general. And if you have things like Spring Web Client, OK HTTP3, or using HTTP headers from Spring, then there is a lot to search across. So they came to us to try to identify usages of that header, regardless of the library used to make that HTTP call. But this is a more interesting problem, because this being search, you can't simply sample to limit your search page. You actually have to look across all the method invocations that you have. So our solution then was to use an embedding model to find which method invocations were more closely related to the query. But we have the same challenge with speed again. This being search, results should appear quickly. So again, say that we're looking across some 1,200 repositories from Netflix, Spring, and Apache. And we have to look at each method invocation. And say we have a somewhat small latency to look at these, which takes about 10 seconds each. Then the whole one search would actually take 10 hours to complete. That is insane. That is not something that we can run at scale. So what can we do then? Well, we looked at doing a top K, because when there are 364,000 method invocations, you can expect that some of those method invocations are the same method with different arguments, or sometimes even the exact same arguments in a different location. So if we can go and get all method signatures and retrieve the top K, with K being a high number like 500, then we were able to significantly reduce the latency. So then this is the model that we, the pipeline that we ended up with. We have a recipe which has a few different models as sidecars. And using a scanning recipe from the OpenRewrite framework, we have an accumulator that visits all methods invocations and then grabs all method signatures for them to essentially deduplicate. And really, we put those into a priority queue based on the distance of their embeddings and the user's query embeddings. And the closer these embeddings are, the more they are related. And you can use either the angle or the pure distance, but it depends on how the model was trained. We, in this case, use pure distance. And once we've visited all method invocations, we go and visit them right back, but this time with the priority queue already populated. So we go and visit the files and use a method from the, and if the file uses a method from the top 100 or 500 recipes, methods, then we use 3 different models and we chain them together from the smaller to the larger ones. And we only call the next model if a match is hard to determine from that model. So you have a small one which says a clear yes or no or I don't know, and then you continue with the one, and then the ones where you're not sure, you take the next model, which again says a clear yes or no, or I don't know. And that way you're able to limit the search space quite easily in this method. Now the last model is a generative model, for which we ask, are these two related? And then take the probability for the next word generated to be yes as our threshold. With that recipe, we were then able to help our customer find all the different web client libraries that they were using, and even a few that they weren't aware that they were using. And from there, they were then able to target these for transformation to get out away from their identity access provider, helping reduce their costs. So then let's try to wrap on all of that we've seen. You've seen a couple of different ways in which we use AI at Modern for our users and our customers. You've seen how we have our LST model helps facilitate targeted search and replacements to fix those misencoded French characters. You've also seen how we use recipe embeddings to help improve our search. And next we looked at how we can use generative AI to formulate recommendations and limit the search space by using clustering and again using embeddings, but now on method declarations. We feed those recommendations into the search that we already built previously to get out the recommended recipes. And we'd like to build with these Lego blocks that use AI and some that don't. Being able to separate them, we can test them individually and reuse them later, and therefore be more efficient. It's like if these AI Lego blocks are the new microservices, composable things that you group together and help you go faster. And this chaining of individual components is a common theme in our research on AI, to offset the unpredictable elements of some subcomponents. That way we're able to get predictable results from unpredictable inputs. Now there's a few takeaways from this, our work on AI. And the first is that AI at scale is pretty difficult. You need to safeguard it in a way that makes sense. If AI is like having 1,000 interns and you have to review all the work that those interns are doing, then you're still going to be limited by how well you can validate things. So find a way that you can do that verification in a way that you trust. And for us, that was very easy because we have those recipes that do the actual code changes. Now, another takeaway is that there is a two-part cycle to integrating AI. And as first part of that, you need to very thoroughly test your methods. And then I mean the research part of methods. So a tip is to look for a benchmark for the best candidate models that you want to use, and then test them on a set that you curate yourself. When we did the recipe search, we had some 20 queries that were handwritten and the match that they should result into. And that way we were able to quickly test a bunch of models and to see how they matched our framework. Actually deploying AI into production is something that can be quite challenging. There's GPUs are very expensive and CPUs are very slow for using these models. So a good way to try to test this out, if you're able to do these types of deployments, is to start with the very simplest thing. Write a Python script that returns always returns true, and then try to get that to production. Is it able to actually run in such a way that you're able to call out to that one, get a response, get it back, and present the results from your Java or Spring applications? And this kind of flushes out any of the issues that you might have in your infrastructure to be able to then do something more intelligent. Now, a final takeaway is that try to use pre-trained models wherever you can. Training a model is very expensive, and it takes a lot of effort to design a good training set. And additionally, there are a few companies that can host those models for you, like Anthropic or OpenAI. But for us, this was not an option, because again, we have some customer tenants that cannot make these calls to external services. But if that's an option for you, that is definitely something to consider. So, if you want to learn more about any of this, then I recommend these individual resources. So if you want to know about how we can support your Spring Boot migrations, then go to docs.openrewrite.org, and we will help you through the whole process of running recipes and even creating your own. Now, I already showed you some blog posts, but we have some more on there and some new ones coming out, where Justine goes into more detail to tell you how we are doing all of this type of work. all of the work that we're doing on OpenRewrite, even the research that Justine is doing, is available at github.com/OpenRewrite. And then we also have a YouTube channel if you want to learn more about specifics or topics related to OpenRewrite or Modern. And then with that, I would like to thank you all for your attention.